Okay, so I see about 80% of the Rob 501 class is looking for a job today. It's all good. It's all good. Just remember, I get a tithe of your income, okay? All I need is 1% of everybody and I'm set for life. Okay, let's review where we left off. It's pointed out that I wrote at the end of last lecture in a fit of madness and being in a hurry that the field was R2×4. Matrices cannot form a field. It has to be the vector space. So thanks for this being pointed out at the very, very end of last lecture. So we got through a couple of key things. Very, very important, a linear combination cannot be infinite. It has to be a finite sum because we do not know what a limit means in an arbitrary vector space. It's that simple. And when you write infinity, you mean a limit. The most important concepts we went into was linear independence and its opposite, linear dependence. So linear independence is about having a set of vectors. You're looking for a solution to the equation where the unknowns are the elements of the field. And you're trying to write that as the zero vector. Clearly, alpha 1 equals alpha 2 equals alpha 3 equals alpha k is always a solution, and that's called the trivial solution. When that is the only way of getting 0 out of the vectors, they are said to be linearly independent. And then otherwise they're dependent, and that means there exist alphas, at least one of them not 0. So they're not all 0, such that I can get this equation to add up to 0. So that's dependence. So roughly speaking, one of them is at least redundant, okay? Heuristically speaking. We had studied earlier in the week the notion of a subspace and how to check for it. The thing we introduced was a span, so you take an arbitrary non-empty subset of your set of vectors. Could have one element, it could have 5 elements, it could have an infinite number of elements. The span is the set of all possible linear combinations. So since it includes all linear combinations, it's automatically a subspace because it is closed under vector addition and scalar times vector multiplication, because those are the basic elements in forming a linear combination. So it has all those things for all possible k, all possible alpha, and all possible vectors in S. So that's the span. It's always a subspace. So you can take any set that's non-empty and build a subspace out of it just by taking linear combinations. If you're talking about independence of vectors, this is just an observation. We didn't point this out, so it's not really part of the summary. But if one of these vectors is the 0 vector, then I can put any coefficient in front of it and still get 0. So if 0 is one of the vectors in your set, it could not be independent. Okay, because I can put, well, if the field is the reals, I could put 500 there. That would be a non-zero coefficient, and I still get it. So if Vk is 0, any of the elements of the set is 0, then S has to be linearly dependent. Okay, and then just looking ahead, we did a little bit with eigenvectors in in the homework 1, but just look ahead and get eigenvalues and eigenvectors. And there's these notes that are typeset but not proofread. but they're close enough. See page 23. Just review eigenvalues and eigenvectors and then be doing. Questions before we get started on new material? Where are the jobs, Professor Grizzle? No, they're out there. Okay. So some of the stuff today is a little trickier than other things. And so the stuff that's tends to be easier for the Rob 501 students to learn from my experience. I might just paste a few things in and say, hey, read it. And then we can spend more time writing out some of the stuff that causes more conceptual issues. Okay, so first thing we're going to start with is the notion of a basis. So a set of vectors B is a basis for a vector space XF if two things hold. The first one is the set is linearly independent. And the second one is I can generate all of the vectors in X by doing linear combinations of B. X equals span of B. Okay. So this is a basis of a vector space. There are enough elements in here that I can generate everything in X by just doing linear combinations of these. And there aren't too many of them that it becomes linearly dependent. So, okay, so there's no redundancy in the set. So let's just do examples and non-examples. So the first one, these are called the natural basis vectors. And you'll see why they're called natural. Whoops. Ding. So if we take the n tuples over any field, or we make the choice to be specific to any of our favorite fields, we have exactly the same natural basis vectors. E1 is 1, 0, dot, 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 0, 0. E2, 0, 1, 0, dot, 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 0, 0. En, 0, 0, dot, 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 0, 1. Okay. Often you'll see them with the E subscript 1, subscript 2, subscript 3, whatever, okay? I'm putting superscripts. These vectors are clearly linearly independent because if I do alpha 1 plus alpha 2 plus alpha 3, I just get alpha 1, 0, alpha 2, 0, alpha 3, 0, etc. So, and how do I write a vector that has alpha 1, alpha 2, dot, dot, alpha n in it in terms of these? Just alpha 1 times this and alpha 2. So it's the span is everything. So that one's real easy to check. Okay. They're linearly independent and they generate everything there. So they're a basis. I can't read that, so how can you? let's take the n tuples of complex numbers with the reals. Okay. Well, since I only have the reals, if I just have E1 through En, I cannot generate any vectors with complex entries. So J times E1, J times E2, J times En is a basis. Whoops, I already got that, a basis is. Okay? Linear independence over R, and then the span, it's immediate to check that. Three, let's do our set of polynomials with real coefficients. And in fact, whoops. The set of monomials is a basis, okay? Remember, this is all polynomials with real coefficients, P of t, and that's a basis. Let's try a few non-examples. Oops, thought I had red, but I don't. Okay. So let's go back to CNR. Then if I take the natural bases for RNR, this is not a basis because if I do the span of these set of vectors, I don't get all of Cn. Okay. How do I know that? Well, J times E1 is not an element of the span Okay, so the field is important. If I was doing Cn and the complex numbers, then I can generate any complex n-tuple by taking the span with the coefficients and the complex numbers. But because I'm doing it in the real numbers, anything with an imaginary coefficient in front cannot be generated. So the span is not everything. So it depends on the field. Okay, and then let's do CNC, the set E1, En, JE1, JEN is not a basis because okay, so I'm allowed to use complex coefficients when I build my linear combinations. So if I take the span of this set, there's no problem. I still generate Cn, but it fails the independence, okay? JE1 is simply J times E1, so there's a simple equation. Minus JE1 plus 1 times JE1 equals 0, okay? So there's a non-trivial combination that gives 0, so because the set is dependent. Okay, I'll write it all the way out. We don't have a nonlinear dependence, but I'll still write linearly dependent, okay? Yes, question?
Yeah. For your first non-example, you used the complex and the reals for this set, but for your second basics example, you obviously use the same. What's the difference there?
I have the same vectors.
No, the one before that.
Oh, this one? Yeah.
You also use CN and R.
Yes?
So how is that a basis and the other one's not a basis?
Okay, so this is now a basis because with just doing real numbers, you give me, so let's go back to CNR. Let me do C2R, okay, because I'm lazy. Let's do X equals 2 plus J minus 4 minus 6J. Okay, so that equals 2 times E1 minus 4 times E2 plus J times E1 minus 6J times E2. And so here's basis vector 1, basis vector 2, basis vector 3, basis vector 4. Okay? And they're linearly independent with respect to the real numbers. I cannot write JE1 as a linear combination of these just using real numbers. I need the complexes. Question?
So with either the natural basis vectors in your last example, would they be a basis if you just use E1 to En, or you just use JE1 to JEN?
Yeah, so with C2R,
Or no, for CNC.
oh, CNC, yes. So CNC, you just need the natural basis because my complex coefficients, let's just do the same example with C2C. C2C, I can write X equals 2 plus J times E1 plus minus 4 minus 6J times E2. I'm allowed to use complex coefficients. Yep.
I'm still confused how in the first non-example that's not a basis. It's CN to the R, CNR. It seems like you wrote the same thing.
No, here I can only take real coefficients, so these are linearly independent, but they don't span Cn. This vector is not in this span because I'm only taking the span with real numbers.
Okay, but you have that same thing written above that says it is a basis. Can we just do that? CNR.
But the field is different, okay? Yeah. So unless I made a really bad typo, FNF, n tuples over a field, so Rn, Cn, Qn, etc. This is a simple basis,
Yes,
okay?
that makes sense. And then CNR is a basis, but you just showed us out.
CNR, I have to add more vectors to get a basis. Yeah, because I can't generate JE1 with just these vectors by doing real coefficients. Yeah. Yeah. No, let's come to office hours. We'll go through it. It'll one little couple things and it'll just sink right in. But here the main thing is what coefficients can I write in front of the basis vectors? That's what determines what I can generate. If I limit this to real numbers, then I can't generate 2 plus j, okay? It's not a real number. So the field matters. Okay, so. Now we're going to make a super slick definition. And I hope you like it. Dimension. And if you've had a course that does it this well, I'm totally impressed, okay? How about that? Definition. Whoops, I wanted black. I'm not getting them easily. Definition. Let n be bigger than or equal to 1. Be a finite integer, just to be extra clear. I could have said, let n greater than or equal to 1 be a natural number, okay? But I didn't. Too bad. xf has dimension n if two things hold. A, there exists a set of n vectors in X that is linearly independent. Oh, come on, slap. Be nicer to me. B. My battery must be getting low. I'll fix it later. B. Every set of n plus 1 vectors is linearly dependent. Okay? But you write it down, discuss a second. We'll also define infinite dimension, and then we'll do examples. So if X is going to have dimension 8, I have to be able to at least find 8 independent vectors, at least, okay? If the dimension is going to be precisely 8, if I get 9 vectors, it has to be dependent. Okay? So if it has dimension n, I can always find this number of vectors, and whenever I add even one more to it, it automatically is redundant. I don't need one more vector to generate linearly independent sets. Okay. Yep.
Why don't we use the number of the elements in the basis of this space?
Oh.
The last one.
Yeah, so the question is, and I've been waiting for that question, thank you. And I will answer it in just a second, okay? So let me finish this and then we'll get to that. Okay, and then definition, XF is infinite dimensional if for every n bigger than 1, there exists a set of n linearly independent vectors. Okay. So for n equals 600 trillion, I can find a set of vectors with 600 trillion elements and independent, and I go 600 trillion and one, and I go exponential of that, and I go times Avogadro's number, I can still do it. It's infinite dimensional, okay? The question was, why do I not say that the dimension is the number of elements in a basis? Question, does every vector space have a basis? Okay. So the notion of a Hamel basis, it is equivalent to the axiom of choice. It's one of those super deep things in mathematics, okay? So in fact, every vector space does have a basis, but that satisfies our definition of a basis. The set is linearly independent, and then you get the span. But proving that, so what is a basis for the set of all functions that map the interval 0, 1 into the reals? Give me the basis for that. It's a very simple vector space. Okay? It has a basis, yeah, we'll get to you, but it's not easy to prove it has a basis, okay? So then I can't just say it's the number of elements in a basis, because I can't, you know, with our mathematics, we can't prove it even has a basis. But we know in the set of functions, say from 0, 1 into the reals, the monomials are all in there and they're linearly independent. So that set is infinite dimensional. Okay, so that's why this definition is like brilliant, okay? It's not necessarily mine, but still I love it, okay? So this definition is set up so you don't have to worry about existence of bases. It's just something very fundamental. It's based on linear independence. Question? Yeah?
When you have the example, the complex numbers x and then the field is over the complex over the reals.
Yeah?
And you said the basis vectors, the basis was E1 through to En, and then J1.
Mm-hmm.
So what does that mean for its dimensions? Is its dimension not N?
The dimension is 2n. Mm-hmm. Yeah. CNR, as one of our examples will do, it has dimension 2n. Here is a set of 2n vectors that is linearly independent. So it's at least 2n. Maybe it's 5n. Maybe it's 100n. But you add one more vector to that, and you can always write it as a linear combination of those. So it becomes dependent. Question?
Is it ever possible to have, to like satisfy the first condition, but not like the second, like find a basis that's smaller than the number of dimensions?
No. Okay. But the main thing is, let's take it offline so we don't, but it's really tied to dimension is the maximal cardinality you can get with linear independence. So that's why it has to be equal to, okay?
They don't have to span.
Well, for it to be a basis, the span of the set has to be all of the vectors. So we will prove something that will get to the heart of what your question is. So, others? Okay. I'm glad you guys are thinking. That's fun. Okay, so let's do some examples. Another question? No? Fun? Yeah, come on. This is super fun. Examples. 1. Dimension Fn, F, it's n, just like you want it to be. 2. Dimension CNR, that's 2n. 3. Dimension, set of polynomials with real coefficients, and the field is the reals, it's infinity. Because the monomials form a basis, and they have an infinite number of elements. 5, dimension the reals as the vectors and the rational numbers as the scalars. Okay? First of all, I'll once again ask the rhetorical question, what is a basis? Good luck. Okay, I don't know. It has one. What's the dimension? 3? Is it fractal? No, it's an integer. Or is it an infinity? It's infinity, okay? Not on any exam, okay? So that's one of the reasons I want the rationals as one of our potential fields, because it gives these really bizarre examples that make you think about something fundamental like, oh, the dimension is the number of elements of a basis, which is what most of you have been told in other classes. So I totally get it, okay? But, okay, fine. To calculate the dimension here now, you need to first give me a basis. Have fun, okay? Have a lot of fun with that, and then count up the number of elements, yes?
So how come it's hard to show that like for n, there's an n plus 1 set of vectors that are all
So
just as hard?
that is not easy. And you need to do a little bit of algebra, yes?
So this definition you gave for infinite dimension, is that different from what is usually the typical definition in classes that just number of?
Well, I just said that you can keep finding sets of larger and larger dimensions, so by an inductive process, okay? So that makes it very easy for P of TR because I know 1 T squared, Tn is independent. I add Tn plus 1, it's independent. I add Tn plus 2, it's independent. For every n, I can find a set of vectors that's linearly independent. Now, for R and Q, I have no idea what those vectors are. I don't want to know. I don't want to do the process, but I want you guys to go play on Wikipedia and find out, okay? But I don't want to do it. Yes, question? It's going to be things like that, yeah. Yeah, so that's the process, but it takes a lot of work to make it go. I played with it and said, forget it. I got to do something that'll earn me some money, okay? So, okay, but that helped get the idea. Question?
So I remember Q is a set of
rationals.
R is a
Yep.
Get an irrational number from the set of rational numbers.
All the irrationals are here. The reals have them, okay? The problem is finding a basis so that I can write every number as a linear combination over the rationals. So there's going to be irrationals in the basis for sure, because irrational times a rational is often an irrational number. Okay, so it's going to be a gigantic basis. It's going to be the same infinity as R. It's not the infinity of the integers. Okay, so it's just out there to make you squirm and have a little bit of intellectual fun. That's all it's there for. But it's not practically important as an engineer. But as a human being, it is fun to have stuff like that, okay? So to be human and to be a Rob student, and for a cocktail party, it is great conversation, okay? Especially after that second beer, okay? So anyway, I didn't say that. No, I did. It's on film. I keep forgetting, okay? Okay. Oh, come on. Okay, images today.
Come on, open up.
Basis uniqueness. No. Basis theorem. That's what I want. Okay. Okay, done playing with it. Let's use this. So here's the thing that you guys know in your heart is true. If I take a finite dimensional, n-dimensional, so n is some finite number, an n-dimensional vector space, then I take any set of n linearly independent vectors, it forms a basis, okay? So I was just showing you examples with the natural basis. Okay, so we just take this set that's linearly independent. What do we need to show to make it a basis? Well, we need to check it's linearly independent. Well, no, it's already given, okay? So we just need to check the span condition. So we just take an arbitrary x. Can we find coefficients in the field such that I can write x as a linear combination? Then everything in x is in the span, because this is the span. These things like this are in the span. And so all we do is use our definition of dimension. I put in x in this set, it has n plus 1 elements. Hence, it is linearly dependent. Why is it dependent? If it were independent, then the dimension of x would be n plus 1 and not n. Okay? So that's how you get it. So the dimension of x would have to be bigger than n, which it isn't. So I can find coefficients, not all 0, because the set is dependent, such that I can write this equation. Now, what we want to do is simply move all of this to the other side, divide by beta 0, and write x as that linear combination. We want to do it. Well, moving everything to the other side, that we can do. But we cannot divide by 0, so we have to show this coefficient cannot be 0. You see the strategy? I don't want you writing it down. I want you just thinking about the strategy. Well, let's suppose it is 0. Does that lead to something stupid, a contradiction? So suppose this is 0. Not all of these are 0. So if this one is 0, one of these is non-zero. Okay? That means this set is linearly dependent. But it's not, okay? So it cannot be the case that beta 0 is 0, because then we get that V1 to Vn is linearly dependent. So then we can just do what I said we wanted to do, and then everything is fine, and we have our new coefficients, okay? So go through the proof at home, but it's just, can I divide by beta 0? Only if it's non-zero. So prove it's non-zero using the hypotheses you have, and everything is done. So it's a super slick little proof. That one is mine, haha. Okay. I'm going to paste this one in as well, because it also seems to go fairly well. Once again, the whole idea is to spend more time on the things that are fun, like does every vector space have a basis? What's the dimension of Q, R with Q, etc. Okay, so this is a uniqueness, and we're going to use the word representation pretty soon. Representation, but not quite yet. So let's suppose I have a vector space and I have a basis. So remember, basis means linearly independent and span, okay? Suppose I have x in there, and I write x as a linear combination of those elements, and then you come along and you write it as a linear combination as well. So these are my coefficients, these are your coefficients. Do they have to be the same? Can we find different ways of writing x with the same basis elements? Or are they unique? That's the question. My answer match your answer? Yes. Okay? Then the coefficients are all the same. There's only one way to write x as a linear combination of the basis elements. That's what that says. Okay? Only one way to write x as a linear combination, so just leave some space in there, but this is the takeaway, of the basis elements. Okay, so instead of writing everything down, just leave yourself some space. You can measure roughly what you need. But how do I prove that these things are the same? Well, yeah, question. Okay, cool. Anything else that's pressing? It's all cool. Sometimes I don't see everybody. I apologize. Okay, so I don't know yet that these are the same, but I know x is the same, okay? It's the same x on the left-hand side. So 0 is x minus x. That's part of the definition of a vector space, okay? So I write x one way, and I write x another way, and then I just add up the coefficients on B1, I add up the coefficients on the second basis and the kth basis element, okay? So 0 equals this, but these guys are from a basis, hence they are linearly independent. And the only way I can write out 0, the 0 vector, in terms of linearly independent vectors is if all the coefficients are 0. And so once the coefficients are 0, then alpha I equals alpha bar I. So my expression of x in terms of the basis elements is the same as yours. Okay, so just linear independence gives the uniqueness of writing x in terms of a basis. Okay. Okay, so we will call that expression a representation. So I'm going to make that definition now. So representations of vectors. Okay. Or how we can do most of our abstract linear algebra calculations in MATLAB, okay? And if you don't like MATLAB, put any open source matrix manipulation tool that you want. I don't care, okay? This is just my euphemism for numerical calculations. Okay? So, oh, your question. I didn't come back to you. You figured it out? Perfect. But once again, I apologize for not coming back. So let x, f be an n-dimensional vector space. Okay. I'm going to write it the basis and give it a name, and not B, and you'll see why. Okay, so, as we knew, n-dimensional, we have n basis elements, okay? But we just can't use that as a definition because we don't know how to handle the infinite case and things like that. Okay? And let x be an x. Okay? So if I take my x, I can write it as alpha 1 times v1 plus alpha n times vn. And this is unique. Okay. But I can also just take those coefficients and stack them up and get me something in the set of n tuples over the field. Okay? Maybe I can't change colors anymore today. Oh well. Okay, because my expansion is unique, I can associate to every vector in the vector space an n tuple once I fix the basis. Different basis, different expansion, but I fix the basis, I take a vector, it's my abstract vector space, I can replace it with n tuples. Okay? Try one more time. Yay! Definition. Alpha 1, alpha 2, alpha n is the representation of a vector, of my abstract vector x in my vector space x with respect to a basis v equals v1 to vn if I can write x as alpha 1 v1. I don't know why sometimes I do 2, sometimes I do 3. Okay? So that's the definition of a representation with respect to a basis. Okay? This is the end. To emphasize the dependence on the basis we will often write it like this. Okay. The representation of x with respect to the basis v equals alpha 1, alpha 2, alpha n. So, okay, so I have my vector space. I build a basis for it. I take an abstract vector and I write it in terms of the basis then each vector is associated to just a set of scalars that I've stacked up. So these are my n tuples. So when f is in R, this is in Rn. When f is in the complex numbers, this is in Cn. Okay? So even if I've got a finite dimensional set of functions, I take a basis for it, I can do all my calculations in Rn if they're real valued functions. I'm going to do an example with matrices. I can still convert that to calculations in Rn if they're real valued matrices, okay? Questions? Kind of cool? Please. Say louder, please. Yeah. Remember, part of Rob 501 doesn't have to be an advantage. It's just we try to do abstract nonsense and you get credit for it. I know it's not very satisfying. We will see the advantage of it. So what it allows us to do, for example, I will show you how to differentiate functions based upon data using matrix multiplication. Yeah, that's going to be cool, okay? It's awesome. So I can reduce something that you think is really hard, but now I'm sitting on my robot and I just got a stream of data coming in. I can get the derivative of the encoders by just matrix multiplication. So you need this way of thinking about functions, which you might think of that function as being a sum of sinusoids and cosines, like a finite Fourier series. And I can calculate its derivative, which is matrix operations. So it's very quick to program and boom, okay? So that's the ability to abstract from these guys to something very concrete that I program up in MATLAB, C++, Python, whatever your favorite language is. That's what I'm showing you how to do. But I still want you to believe in the first answer. We love abstract nonsense, okay? It's all grounded, everything we do is grounded in something that you'll see in other courses and be really satisfied with, but you will leave Rob 501 thinking I just taught you abstract nonsense. Unless you have faith in me. Faith, that's not easily won, is it, Professor Grizzle? No, it's not. Come on, come on. Thank you. Okay, basis example, vector representation. Okay, you don't want to write this all down. Just save some, oh, come on. Cancel. I'm in a limit cycle here. Hey, I got out of it. Okay. Okay. So this is not functions, but whoa, that's not good. Okay. These are not functions, but it gets the basic idea of representation. So our abstract vector spaces are 2 by 2 matrices with real coefficients, and the field is the reals. The first basis you might call the natural basis for these matrices, okay? V1, V2, V3, V4. But if this is a 4-dimensional vector space, because we know that that's independent and it spans, if I take any other 4 set of vectors and I check that they're linearly independent, then they span as well, okay? So I can write X, 5, 3, 1, 4 in terms of the natural basis. That's super trivial. 5, 3, 1, 4, okay? So the representation of X with respect to the first basis is just 5, 3, 1, 4. All I did was take the elements and stack them up into the vector, okay? So that one's not very interesting. Now what takes a little bit more work? What if I take the matrix 5, 3, 1, 4 and I want to write it in terms of this W basis? Okay, so to do that, make a little note for yourself. You have 4 simultaneous equations. Okay, so you're writing 5, 3, 1, 4 equals alpha 1, and then I have my bases over here. So 1, 0, 0, 0 plus alpha 2, just to make clear what you're doing. Three, 0, 1, minus 1, 0, plus alpha 4 times 0, 0, 0, 1. Everybody see the 4 equations and the 4 unknowns? You do alpha 1, alpha 2, alpha 3, alpha 4, and that adds up to 5. And then you do alpha 1, alpha 2, alpha 3, alpha 4, that adds up to 3. So there's 4 equations, 4 unknowns. And you have to solve them. Okay, so doing expansions in general, boring, okay, but you just do them all with MATLAB, okay? So you never do them by hand. On an exam, they have to be so simple that you can't even mess it up under stress. You believe me? I'm pretty straightforward with you guys, okay? So my assessment of your worth will not be how fast you can solve 6 simultaneous equations, okay? I don't care about that in Rob 501. I just want you to know what are the equations that you need to solve, not your ability to quickly solve it. So, okay. So that's how you find this other representation. So you change the basis, you change the representation. You change the basis, you change the representation. So, 1. Okay, let's go back to this simple basis, okay? What if I change these such that it was V1, V2, V3, V4? So I just shuffled the order, right? I still have to write it out, but instead I get 5, 1, 3, 4, right? I shuffled the order, the coefficients get shuffled. I changed the basis, so I changed the ordering of the basis. So this is a comment that is tied in with the Nagy book, okay? So the order of basis is given, or I should have said in which the basis is given, but I'm going to blow my preposition here, matters. Nagy calls a basis written as V1, V2, Vn, and ordered basis. Sets don't have order. Yeah. So for us, it's really a list. It's not really a set. It's a list. And we've labeled them the first element of the list, the second element of the list, the third element of the list. In Rob 501, all bases are ordered, okay? At least the finite dimensional ones for sure. Okay, so when Nagy, this book that we use for our thing, says ordered basis, read basis. Okay, so when Nagy says ordered basis, it's the same thing as basis. That's it. Ordered basis, basis. For us, they're the same thing. We just call it a basis. So just a remark. How we doing? Okay, can I paste in some more stuff that's easy, or do you want to keep writing? Okay, I'm going to do what I want to do since nobody's going to stop me. Let's see, easy facts, how about that? That's got to be fun. No, don't do it. Okay, so if I sum two vectors and calculate their representation, okay, so I sum the two vectors and I find the n-tuple, okay, or I first find the n-tuple of x, I then find the n-tuple of y and I add them together, I get the same thing. How do you prove it? Write x is, alpha 1, v1, whatever in the basis, write y, etc. Write the representation, just you'll get the alpha 1 plus beta 1, all this stuff, okay? So finding representations is linear, it's additive, okay? But if I double the vector and I compute the representation, it's the same thing as I first computed the representation and then doubled the representation. So all of my rules of addition of vectors and scalar times vector multiplication in the abstract vector space carry over precisely to the n-tuples. They're the same. They're the same vector space, you've just written them down in a different way, okay? Maybe one is easier for calculations, like extracting a derivative from data, okay? That's the key thing, okay? So I've got it summarized there. Let me write it down as a kind of a formula. XF, once you make a choice of a basis, it's the same thing as the n-tuples. So we will want to be able to do things with abstract vectors, but we want to do the calculations in MATLAB. We do all the calculations there, we get the answer, and then we just reconstruct the abstract vector by taking these coefficients times the basis vectors. Okay, going from here to here, that's easy because it's multiplication. Going from here to here is solving simultaneous equations. So one way is really easy, okay? Okay, now this is the hard topic of the day, change of basis matrix. This is the hard one. But if we get this rule down when we do bigger things like linear operators so that we can find a way to do differentiation with matrix multiplication. If we get this one down, then the next one's going to work. So here's the idea. Let U1 to UN be a basis for XF. Yep, it's n-dimensional. Let's take another basis. I'm just going to label them with a bar. And it does not mean complex conjugate. It's just a bar. Be another basis. What is the relation between the representation of a vector x in the bar basis and the representation of x in the first basis? Okay, we're working with a vector space. I do all my calculations in the n-tuples with this basis. You do all your calculations in the n-tuple with this basis. How can we transform my answers into your answers? And vice versa, okay? Without going back and redoing everything in the original basis. So the answer is, it's just a matrix multiplication, okay? So here's the super cool theorem. Theorem. There exists an invertible n by n matrix by n matrix P with coefficients in the field such that for every abstract vector in our vector space, okay, the representation of x in the bar basis is equal to just p times the representation of x in the unbarred basis. Remember, I choose the basis. This is now an n-tuple. This is now an n-tuple. This is an n by n matrix. So it's easy calculations, okay? Now, how do you calculate that matrix? Moreover, we calculate P by its columns. We decompose it in terms of its columns. With the ith column of P is simply we find the representation of the ith vector of the original basis in terms of the new basis. Question, yes?
So is that matrix number the basis for that?
Say that louder.
So like, sorry.
No, it's okay.
Is this matrix, you have these columns, are they now a basis for?
Well, the columns here, because the matrix is invertible, these guys are linearly independent. They are in Fn, so that is another basis for Fn. Yes, but that's not needed in stating this result, but it's true. Okay, so We'll do the proof, and then probably the example will follow, but we'll see. Let x be an x. Hence, I can write x as I equals 1 to n alpha I ui. And I can also write it in terms of the bar basis. Why? Because they are bases. Whoops, there's a bar missing on this one. There we go. Keep me honest. Okay. In our notation, the representation for x in the u basis is alpha 1, alpha n. Sometimes I'll just call that alpha. And the representation of x in the bar basis is alpha 1 bar dot 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 alpha n bar. Okay? Sometimes I'll call that alpha bar. I know this seems super abstract. It's going to become second nature in a week, I promise you. You don't believe me, it's going to become second nature, okay? So remember, this is just an n-tuple, this fancy notation, abstract vector basis, n-tuple, abstract vector, same abstract vector, a different basis, a different n-tuple. I want to find how the two n-tuples are related, okay? So alpha bar is the representation of x with respect to u bar is the representation of x. Let me just write it in terms of, okay? Right? I got this guy by expanding x in terms of the bar basis and n-tuple. So I'm just going to replace x now with this expansion in ui, u bar. But this representation is linear, and so this is equal to sum I equals 1 to n alpha ti times the representation of ui with respect to u bar, okay? Representation of the sum is the sum of the representation. The product of a vector, a scalar multiple times a vector representation is just a scalar multiple times the representation of the vector. So I just use linearity and skip the induction step, okay? Okay. Now this guy, that's what I define to be the ith column of P. Now you write that down. That was my definition. The ith column is this n-tuple, the ith basis vector in U with respect to U bar. Okay. So this equals sum I equals 1 to n alpha I pi but because we understand partitioned matrices, okay, so it's a linear combination of the columns of pi, and so we just write out p, we write out those coefficients, that's the same thing. P times this vector is this linear combination of the columns. So this is P times alpha. alpha bar equals P times alpha. The ith column of P is the representation of Ui in U bar. Silence of, I feel oppressed, Professor Grizzle. You're just imposing all these symbols on me. Okay? Let's just wrap it up, and then we'll go home and we'll pick up on Thursday. But okay, I say that P is invertible. From this formula, you can't tell anything about the invertibility of that matrix. So let's just settle that. Okay? Okay. Okay, by the same reasoning, we can write alpha, equals P bar times alpha bar. Okay, so we just flip the expansion around. Hence, alpha bar is P times alpha equals P times P bar times alpha bar. That implies P times P bar is the identity. And then alpha is going to be P bar times alpha bar, and that'll be P bar P times alpha. So conclusion, P bar is the inverse of P. And hence P is invertible. Yeah, the question is, do we need to show both? And for the definition of an inverse, you do. And then there's certain types of fields for which once you have one and you have a full rank condition, then the other one holds, but this is the easiest way to show it. This is the definition of invertibility. Yes? Yes, we do need it square, but P has n columns, and each column is an n tuple. So it's n by n, as claimed. Yep. Yeah, I skipped that, so sorry about that. Yes, you should show that P is square. Okay, so in practice, we can go back and forth. And then what we do is we always compute the easiest one. Okay? So if I want to go and calculate this matrix, it could be that P bar is easier to get, and then I get P by inverting P bar. So instead of rushing through that, we've got only a minute. I will post the example in here, but we will go through the example first thing on Thursday when we recall what is a matrix representation. Excuse me, a change of basis matrix. Okay? Thank you. Office hours, I'll be upstairs in like 2 or 3 minutes.